Now we're going to talk about one of my favorite topics, polynomials. And I've called this polynomial expressions to cover all the possibilities. But polynomials are wonderful. As you'll find out later, they're called functions. But we're just going to look at them as expressions right now. The first thing we're going to answer is, what is a polynomial? Because that is the essential idea at the beginning. And then we'll see what we can do with these things. So, what is a polynomial and why the funny name? Well, poly means many. And it will include, of course, includes one. So we cover all the cases there. And the nomial part, there actually is a word that's based on nomial, but we can think about this as just terms. Okay? There'll be terms of a certain kind, as I'll explain. And poly, you've seen, it means many. You've seen it in other words like polygon or polyglot, a person who speaks many languages. But what we will do here is, because we don't want to do many first, we'll do one first. We start with a one-term polynomial. Okay, so we start very simply, and we'll work our way up to the general case. So here's the definition I'm going to write down. And the next page will have even more, but I can start it here. Definition A, well, what will I call it? If that was poly, we'll use another root from a dead language. Polynomial. We'll use monomial. A monomial has the form, and I'll go to the form on the next page. Why do I call it monomial? Well, you see the word mono there, which stands for one. You've seen the word mono in other words like monorail or monotone or monopoly or monogamy. All of those words have mono in them, indicating one for some reason. So this is a monomial, and that's the reason for that. Now, it's going to have the form that I'm going to write down here, but I'm going to entitle this page Anatomy of a Monomial in one variable. So we'll explain exactly what a monomial looks like in one variable. It has what form? It has this form. A sub n times box to the n. So I'm going to have to explain all of this, but that's the form. It's a single thing. Notice that it is one term. Terms, remember, are things that are added, and this is one thing that will be added to other things. All right, let's first start on the left here with this a sub n. This is a real number. In other words, it's a constant. It's given a name. It's called a coefficient. That is another piece of terminology you have to learn about polynomials. All the constants that are multiplied are called coefficients. And finally, the subscript, n, is a label. That's all it is. It says, I am the constant that goes with whatever the box power is. So this is the number that is multiplied by something to the n. All right. What goes in the box, you may ask? What goes in the box is a variable. And the variable, of course, can be anything. It can be x, it can be y, it can be u, it can be v, etc. Usual variable letters. So what goes in there is a variable. So we have a constant times a variable to a power. Well, what kind of powers are allowed? This is a power, n. It is allowed to be 0, 1, 2, 3, etc. So the powers in a polynomial do not include negative numbers. Not negative. It's also not rational. There are no fractions there. And it is called the degree of the polynomial. The degree of, of the monomial. We're just looking at a monomial right now. Of course, a monomial is a polynomial. It's just a polynomial with only one term. So I've got a lot on the page here. This is the anatomy lesson. A sub n times a variable to the nth power. This is a constant called the coefficient. This is a variable. And this is the power that's only allowed to be 0, 1, 2, 3, etc. Never negative, never rational. And this number will be referred to as the degree of the monomial. So with that in mind, let's go ahead and write out a few of these so you know what I'm talking about. Here's an example. 2x cubed. There is a nice simple monomial. Here's another one. Square root of 2 times x to the 5th. See, the constant doesn't have to be a nice number. It can be an irrational number. Here's another one that you may not expect. 7. I claim that that's a monomial. Well, you say, there's the constant. Where's the power? Well, remember, the power could be 0. So you can think of this as 7 times x to the 0. In other words, all constants are monomials. You could have 4.36 times y, just to change the variable. You could have 8/9 times u to the 101 power, etc. Those are what monomials are. Constants times variables to powers. Okay. Now that we have these new objects, we ask ourselves, what can we do with them? One of the things we can do is add them, and we'll get a notation for that, a terminology for that. 2 monomials with the same degree, got to have that, with the same degree. Remember what degree is? It is the power of the variable, and same variable. So they both are x's, say, are called, if you have 2 monomials with the same degree and the same variable, they are called like terms. They are terms that are alike in all the essential parts. They have the same variable to the same power. The constant out front may not be the same, but this is the definition of like terms. So ax to the n and bx to the n in general are going to be like terms. The a and b may not be the same, but the the variable is the same and the power is the same. Well, let's see what you can do with those. Of course, you can combine them. We can combine like terms. We have this new phrase now, combine like terms, as follows. Let me give you an example. Suppose you're faced with 2x squared plus 5x cubed minus x squared plus x plus 1 plus 10x. There, how do you like that? Now there's a bunch of monomials added together. Again, our goal in mathematics is not to complicate things, but always to make them simpler. Because if they're simpler, you can understand what's going on and perhaps solve whatever problem you're looking at. All I want to do is simplify this. So what I'm going to do is combine the terms that are alike, in that they have the same variable. Well, all of these share the same variable. That's not a problem. And they have the same degree, the same power. So let's see what we've got, and let's be systematic about it. Let's find out the highest power. That's this one, 3. Is there anything else with the power of 3? No. So 5x cubed here will just stay. Then I look through for squares. There's a square. There's another square. I have 2 things with squares. 2x squared minus x squared leaves me with plus 1x squared. Then I move down from 3 to 2 to 1. There's a 1 power. There's another one of 1 power, an x and a 10x. So I can write down 11x. And finally I go down to the 0 power. That is the constants. I see I have 1 constant here, 1. So I have plus 1. Now in this I have combined all of the like terms. Unless I know more information, this is as simple as I can make this expression. All right. This is now reduced to different monomials. Because if any of them were like, I could have added them. And that's what we wanted to do at that point. Okay, those are monomials. Monomials are polynomials of one term. Now, some polynomials have names. Now, note, a few polynomials actually have special names. Now, why is that? Well, because of history, or because they're ones that turn up frequently. For example, a constant polynomial. What is that? That is, another way of saying that is, it is a polynomial of degree 0. What's next in line after a constant? Well, a n x to the n. Of course, you know that that's a monomial. And what is that? That's a polynomial with one term. All right. Now we're going to go ahead and look at some polynomials and the names for ones with a few more terms. What if you had something that looked like this? You had some an x to the n and then added to it and b m, say x to the m. Now we're staying with a single variable because that's what we want to look at, although there could be different variables. This is two different things. These are not like because the variable is the same but the powers are different. So these are not like terms that can't be added. So this is referred to as a binomial. Bi, as in bicycle. Two things. A binomial. And what is this? This is a sum of two monomials. And since there are many, many cases where binomials turn up, that's why there is a special name for them. Now we're going to look at a lot of simple ones on the next page, so don't get put off by this notation. And let me mention one more. I'll even write the name before I write it. It's going to be called a trinomial. And you can guess what that is. It's going to be a sum of three monomials. Now you can see that this can go on forever. In fact, most of what we will deal with will involve binomials, monomials, and constants. What's a trinomial look like? Well, it's going to be just like a binomial, except there's one more term, say c sub k x to the k. And as I said, don't let the notation throw you. Let me get away from it right now and show you examples of these. Binomials have two monomials. Trinomials have three. That's all there is to it. So, for example, x squared minus 2 is a binomial. 2x plus 3 is a binomial. X squared plus y squared is a binomial. The variables don't have to be the same. So these are binomials. Likewise, just for the record, x squared plus 2x plus 1 is a trinomial. Y squared minus x squared plus 2 is another trinomial. X to the 20th minus x plus 5 is a trinomial. So these are all trinomials. They have three. And for the rest of them, as I say, we just call them generically polynomials. We don't have any special names. Well, on that note, let's define finally a polynomial in one variable. Definition. A polynomial which covers everything we've seen before, even though we gave some of them special names. Polynomial is a generic term. A polynomial in one variable, and today I'll use the variable x, has the standard form, and standard forms, as I've said before, are very important in mathematics, and you'll see that even later. Standard form, and what is the standard form? The standard form is that the higher powers go down to lower powers. You have it organized so that the highest powers of the variable are at the left, the lowest, meaning the constants, if there are any, at the right. And what will be the form? It will be this. A sub n, x to the n. Got to write it out in general now. A sub n minus 1, x to the n minus 1, plus down to a sub 1x plus a sub 0. And you notice when I say these subscripts, I say sub. So a sub n, x to the n. To the means a superscript, sub means a subscript. And these go down. We always assume that an, the original one starting at the beginning, this is called the leading coefficient. Remember, all those constants are called coefficients. This is called the leading coefficient because, well, it leads. We always assume that's not 0 because if it were 0, we could have started the polynomial here with an minus 1. So we always assume that the first one that we start with is non-zero. That only makes good sense. An all the way down to a naught are constants. And again, for us, remember, that means real number constants. And of course, n is called the degree of the polynomial. It is the highest power of x that occurs in this one variable polynomial. So that's what a polynomial is. It really is a wonderful instrument as we work further in the course. But let me give you some examples. Example. These are some polynomials. Here's one. X to the 20th minus x to the 13th plus x. Here's another one. 2x to the 50th. I'm trying to take high powers here to give you a sense of what's going on. Plus x to the 49th plus 5x squared minus 37. How about that? Here's another polynomial. 8. Remember, constants qualify because that's really 8 times x to the 0. So it's a polynomial. In fact, it's a monomial. And then here's a binomial. 97 x to the 100 power plus 1. And so on. You can create as many as you like. The important thing for us is to realize what's a polynomial, these things are polynomials, and what's not a polynomial. Let me show you some non-polynomials. These are not polynomials. Just so we're clear. These are not polynomials. 1 over x is not a polynomial because this is x to the minus 1, and remember, negative powers are not allowed for our x. The square root of 2x plus 5 is not a polynomial because what is inside here? This is square root of 2 times square root of x, which is x to the 1/2 plus 5. We don't allow rational powers, so that's not a polynomial. These are not polynomials. And you might see something more complicated. X squared minus 3x plus 2 over x plus 3. Not a polynomial. It is a rational function, which we'll discuss later. A rational expression. But it's the division of two polynomials, that's true. The top's a legitimate polynomial and so is the bottom. But this expression is not a polynomial. All right. Well, on that note, let's go back to my list, because now that we have polynomials, which are new mathematical objects, we can now do something with them. For example, we can add and subtract them. And this is a very short unit. Watch, there's very little to say. I'll write it out. That'll be the longest thing I do. Adding and subtracting polynomials. This is all there is to it. Just add, or of course subtract, like terms. That's it. That's all you do. And just for the record, let me do one example to show you how this works. And then you'll have a chance to pause and try a lot of this yourself. Here's the example. 3x to the 4th minus 4x cubed plus 6x squared minus 1 in parentheses. And let's subtract from that 2x to the 4th minus 8x squared minus 6x plus 5. What will that be equal to? Well, as I said, all I have to do is combine like terms. So let me walk my way through it systematically. We'll start with the highest power of x I can find and work my way downward. Now I look through here and I see I have 3x to the 4th. Luckily, both of these are written in that higher to lower form. 3x to the 4th and 2x to the 4th. Now there's a minus in front, so it's 3x to the 4th minus 2x to the 4th, so I get just plain x to the 4th. Then let me look for cubes. There's a cube here. There are no cubes down here. So that's the only cube in the problem. Write it down. Minus 4x cubed. Now let's look at squares. 6x squared. In here is minus 8x squared, but there's a minus out front, remember, which goes through the entire parentheses. So minus minus makes this plus 8x squared. That plus the 6 above gives me 14x squared. Moving down to x powers. There's only one of them, it's here. There's none up here. There's only one here. Minus 6x. There's a minus out front, remember, which goes through. So it's plus 6x. Finally, I look at constants, which are the x to the 0 powers. I have a minus 1 above. Here I have a 5 with a minus. So that's minus 5 and minus 1, minus 6. And there I have added these two polynomials. Actually, I've subtracted them, you see. But the addition and subtraction ideas are the same. And now I am finished with adding and subtracting polynomials. So here's what you need to do. You need to practice these polynomial expression operations we've just illustrated. Addition, subtraction, and what polynomials are. Write down a few of them, write down a few of questionable polynomials and see if you can tell the difference. We'll be back in a moment. Now we've looked at polynomials, and then we started performing operations on them with adding and subtracting polynomials. The next two operations, of course, are multiplying polynomials and dividing them. Let's look at multiplying polynomials first. So, multiplying polynomials. Let me first give you a few general remarks, and then I'll do this by example. What is used here, what is at the basis of everything I will be doing, are what are called distributive properties of the real number system, because the variables, of course, are going to represent real numbers. And that just means, for example, if you have 2 times 3 plus 5, that's the same thing as 2 times 3 plus 2 times 5. Because if you do either one of these, this is 8 times 2, that's 16. And what do you have here? 2 times 3 is 6 plus 10. And so those are obviously equal. To bring this 2 across and multiply it times both of those is called the distributive property of the real numbers. The other point I wanted to make here before we get started is it is very important to organize your work. And organizing your work is not to make your instructor happy. It is to make your work easy to read for anyone trying to read it. And remember, you're the first person who's going to be reading it. And you'll be looking back at this work. And you'll be wanting to follow it in case you make errors. So organizing your work is for you and for your thinking. It's not for me. All right. Let's go ahead and look at some examples of multiplying polynomials. And you'll see that there are 2 standard methods of doing this by example. All right. What I want to do, first of all, I'll do a method that I'll just call distributing. Now this is sort of a horizontal method of multiplying. It's a simple idea, and with practice you may prefer this. You may find this to be what you like to do. Let's multiply 2x plus 5 times x cubed minus x plus 2. So I'm taking something simple, a couple of small polynomials, and we're going to multiply them together. Now here's how this distribution works. Whichever one is first, and it probably would pay to put the one with a smaller number of terms first, but it doesn't make any difference. This process works either way. First, take the first term, and now we will multiply it by everything in the other polynomial. Then, having done that, we will take the second term and multiply it by everything in the other polynomial. So if we're systematic, it should not be hard. And then we will add and subtract as we go. So, 2x times x squared, I'll even write that out, 2x times x squared is the first one. Then 2x times a minus x, that'll be minus, or 2x, excuse me, plus 2x times a minus x. Let's leave the minus in there for the moment. 2x times 2, so plus 2x times 2. And now I've finished up with my 2x's. I go back to the 5. Plus 5 times x squared, that's the first term. Plus 5 times minus x. There's the second one. Plus 5 times the 2, like that. Now, of course, if you were doing this on your own, you'd probably collapse some of these operations. 2x times x squared is 2x cubed, and then minus 2x squared for these two multiplied together. Here we have a 4x. Then underneath, I get things that are starting to look like the first line. I get 5x squared. You know what I'm going to do? I'm going to line it up underneath here. Plus 5x squared. This is just for my convenience. There's no not necessary form here. It makes it easier for me. 5 times minus x is minus 5x, and then I have plus 10. Now see, by cleverly rearranging this, I can now just add my like terms easily. See, my like terms are above one another. 5x squared minus 2x squared is 3x squared. 4x minus 5x is minus x, and then plus 10. And lo and behold, I have multiplied these two polynomials together. I've done it by distributing each term over here on the left times each of the ones on the right, and doing it with each term. Now, if you're methodical in your work, this is not very hard to do. But let me show you a little bit more visual way to do this that you might like better. It makes no difference which way you use. I'll write or here, so you see that there's no difference. Now this way, I don't know, you want to call it box, you want to call it by a table, whichever way you like. Here's what I'm going to do. I'm going to create a little box, or a table if you like here. And across the top, let me bring back the polynomial I had, the pair of polynomials, 2x plus 5 and x squared minus x plus 2. Across the top, I'll put the second one. Of course, it doesn't matter which one I put there. I'll put x squared, then in the middle I'll put minus x, and then 2. Remember, the minus should go with the term. It's not, don't consider it an operation sign, consider it a negation. So it's x squared plus a minus x. Put the minus with here. And then the other polynomial, remember, was 2x plus 5. So I'll put 2x here and 5 here. And then I'll just draw in lines separating all these different terms, like so. Now, I just multiply. This row is 2x times x squared, gives me 2x cubed. 2x times a minus x is minus 2x squared. 2x times 2 is 4x. 5 times x squared is 5x squared. 5 times minus x is minus 5x. 5 times 2 is 10. Let me double these lines here to make that look a little better. Now see, I have all the terms I need. I will add everything that's in here. And notice I can add sort of on a diagonal. So the product then, I won't rewrite the polynomials, the product is then 2x cubed. Then these two give me plus 3x squared. These two give me a minus x, and this gives me a 10. Now personally, I like this a lot, because this method works no matter how big the two polynomials are. Of course, if they get bigger, you have more boxes to fill in, but still, it's not very hard to do. It's very mechanical. And that's what you want, an operation that doesn't take much thinking on your part. Okay. Let me do another one, so we can illustrate both of those techniques yet again. Example. We'll take 3x squared minus 2x plus 1 times x cubed plus x squared plus x. So this time I'm taking 3 of each. Okay, here's my first method called distributing. So I will just do it here because I have it lined up. I'll just try to keep track of things. Remember, I'm going to distribute this one times everything over there, then this one, then this one. I'm going to avoid writing the arrows down this time because it might get too messy. So the product will be 3x squared, first thing, times x cubed. Then plus 3x squared again, times x squared. 3x squared times x. And that finishes up my first term. Go to my second, which is minus 2x. So I'll have minus 2x times x cubed. Then minus 2x times x squared. Then minus 2x times x, so minus 2x times x. And then finally I have a 1, and the 1's the easiest. 1 times each of these just brings these back. So plus x cubed plus x squared plus x. And now I just have to pull things together. And let's see if I can do this, see how efficiently I can do this. X squared and x cubed give me x to the 5th. These are all lower. This starts with 4th and goes lower. This starts with cubed and goes lower. So this is the highest power. It is the only power of x to the 5th, so let's just put that down. Let's go to the second one. 3x squared, that's 3x to the 4th. This is lower. Here's another x to the 4th, minus 2x to the 4th. So 3 minus 2 gives me plus x to the 4th. So I've taken care of this one and these two. Let's move down. X cubed, 3x cubed here. This is minus 2x cubed. Any more x cubes? Yep, there's another one. So 3x cubed minus 2x cubed is 1x cubed, plus x cubes give me 2x cubed. So now I've moved from cubed. Let's go down to squares. No squares on the first line here. There's one square here, minus 2x squared. And there's another one here. So I'll have minus x squared as a result because that's plus x squared. Now I go down 1 to x. There's an x here. No x's on the others, so that's the only x. And I'm done because there are no constants. So that's how it would be distributing. Now, let me do it the other way, which again is my favorite. 2 I'll call it a table this time. Maybe that's what we should call it. And let me point out that this works exceptionally well if you always put your polynomials in standard form and then write them higher to lower here, and then higher, that means higher degree, okay, to lower, and then higher to lower this way. That will give you the nice pattern we saw earlier. So let me shade this in, make it a little bit thick there, if I can. Make that one thick. And a little longer, because these are trinomials this time. Along the top, let's bring back the polynomials we started with. 3x squared minus 2x plus 1. I'll put that one vertically. And then, let me push that up here. X cubed plus x squared plus x, I'll put horizontally. So let me write x cubed, x squared, and x here. And then 3x squared minus 2x and 1 this way. And then let me fill in the lines. Draw those lines in there. Now I have 9 things to fill in, but it's very mechanical. 3x squared times x cubed is 3x to the 5th. 3x squared times x squared is 3x to the 4th. 3x squared times x is 3x cubed. Minus 2x times x cubed minus 2x to the 4th. Minus 2x times x squared minus 2x cubed. Minus 2x times x minus 2x squared. And then 1 times each of these just brings them down. X cubed, x squared, and x. And see, if I look diagonally here, there are my x to the 4ths. Diagonally here, there are all my cubes. Diagonally, there are all my squares. The x is alone, and the x to the 5th are alone. So the product then becomes 3x to the 5th plus, and I have my 4ths here, and that's because I put everything higher to lower. See, I get this nice pattern. 3x to the 4th minus 2x to the 4th gives me x to the 4th. All my cubes, 3 minus 2 of them, that's 1 cube, plus another one, plus 2x cubed. My squares, minus x squared, and then my x term, only one of those, and lo and behold, I'm done. Now, I don't know about you, but I like that a lot. I think that's simple, elementary, and very mechanical, and you get the right answer. And you can see how to do this in harder cases with bigger polynomials. But let me be frank. If you had a polynomial of degree, well, not of degree, but with a number of terms that is 4 terms or 5 terms or 6 terms, the best thing to do is to find a computer algebra system and let it multiply the polynomials. Because all you need to do is be able to do a small number of these by hand and do ones that are trinomials or binomials. Otherwise, you can't function in mathematics. You have to be able to do the small ones. But the larger ones, it's impossible to do by hand without becoming nuts. So you want to do those with a computer algebra system. All right, let's go back to my list of topics. We were looking at polynomials, adding, subtracting, and multiplying. And now, since it's such an important error that's made so often, I'm going to talk to you about a common error. It's a common error involving multiplication. So let me go ahead and do this. It's a perennial error among students, and I'm going to show you that it's wrong in several different ways. And I hope you remember this from now on. Here is the error. X plus y quantity squared is not x squared plus y squared. It just isn't so. Why, you may ask? Well, good. I'm glad you asked that. I'm going to give you several reasons. First reason, if it were true, it would work for all numbers x and y. Try x equal 1, y equal 1. 2 easy numbers. What do you get? On the left, you get 1 plus 1 quantity squared. On the right, put a question mark because we don't know yet. 1 squared plus 1 squared. But what is this? This is 2. 1 plus 1 is 2. Square it, you get 4. What do you get over here? 1 squared is 1. 1 squared is 1. Add them, you get 2. Those are not the same number. So if this doesn't work for easy numbers like 1s, then you suspect it's probably not true. But I'm not going to let that convince you. I'm going to do more. Argument number 2. Using distributing or the table method, I will take x plus y squared, which is x plus y times x plus y, and multiply it out. Now this is so simple it doesn't matter which way you do it. Take the x, multiply it by each of the things in the other one, and then add. So we'll have x times x is x squared. That's the first two. X times y is x times y. Then we do y times x, and then y times y. And since x times y is y times x in the real numbers, we can write this as x squared plus 2xy plus y squared. In other words, there's stuff in the middle. This is definitely not equal to x squared plus y squared, because there's something there in the middle that you forgot. Okay, let me show you then one final method, which is a picture. Picture I like a lot. 3. Here's a picture. If neither of the others springs to mind when you try and make that error, this might come to mind. Here I'm going to draw two squares. There's one, and I want the other one to be exactly the same, so hope I get that. Okay, two squares. Now this one, each side is of length x plus y. So there's the x, and maybe I'll make the y look smaller there. This is x, this is y. Make that y this x, and this y, and this x. So the area of this square is x plus y squared. Okay? X plus y is the length of the side. Now with these same lines, let me draw through here. That's why I put the little tick marks here, so I can copy them here. This is still y, and this is still x and x. So that means this is x squared, and this is y squared. This is a square of side x, this is a square of side y. Look at what is missing. So clearly these two pictures are not the same. This white area is not equal to the sum of those white areas. Look at all that's missing. Okay. Well, I hope that those three convince you that this error is impossible. For those of you that want to know about what the situation is in general, let me end up with one final note. In fact, x plus y to the n equals xn plus y to the n only for n equals 1. Because if n equals 1, you have x plus y to the 1, that's just x plus y, and then x to the 1 plus y to the 1 is again x plus y. That is the only number for which this is true. Don't do this in general. And remember, x plus y squared is not equal to x squared plus y squared. So on that note, it's time to pause and practice a little multiplication of polynomials. Now that we've looked at multiplying polynomials, there are certain products that turn up so often that they are really handy to know. So I call those handy polynomial products. And let's go ahead and look at those. So handy polynomial products. Why would one want to look at this? And oh, by the way, these products, remember, you can think of these as identities. And we'll talk more about that later. All right, why would one want these products? Well, when you do calculation by hand, which is the way you're going to do most of your work, at least in the initial stages, when you do calculation by hand, that requires knowing some, just a few, some common, simple products. And you can think of this as vocabulary. Thinking of the language of mathematics now, that's vocabulary. Now, why would you want to know that? Well, just let me remind you what this is like. This is like memorizing the multiplication tables. Remember doing that back in elementary school? And why did you do that? Well, in order to be able to calculate without having to look things up all the time, you need to know a certain number of multiplications. And the same thing goes now with polynomials. If you know some common simple products, you'll be more efficient in what you do. So, let's go ahead and start looking at a few of these. The first one will be the difference of two squares. Difference of two squares. And here is the rule, and then I'll give you some reasons to believe that it's true. X minus a times x plus a equals, and here's the difference of two squareds, x squared minus a squared. So here's the first of the handy product rules. So I'll put handy over here. Now, first of all, to see that it's true is not hard, because you can imagine the distribution going on here. In fact, when we multiply this together using the same pattern we've had before, we take x first and multiply it by both of the terms in the second binomial. So x times x is x squared. That's the x squared over here. And then x times a, well, that's going to be one of the middle terms. So I'm trying to write something here. The middle terms, here's the first one, ax. That's the x times a I just talked about. And then minus a times both of these, minus a times x, minus ax. And then the last one will be minus a times a, and that'll be minus a squared. Well, look what happens to the middle terms. You have ax and minus ax. The middle terms add to 0. So they disappear. And that's the reason over here you just have the difference of two squares and no middle term. Well, I know you believe that, but here's a picture, sometimes called the dissection proof. Because this will give you even more reason for believing it's true, and it's a nice thing to see. So some things are just pretty, so that's the reason I want to show you this. I'm reversing the order here. Notice I'm writing the difference of the squares on the left this time. X minus a times x plus a. Now, I'm going to give you a picture that I hope will help you visualize this. For x squared minus a squared, imagine a big square minus a little square. So in the picture, we'll have the big square, and then down here in the corner, the little square missing. So if this is the big square xx, this is the little square AA, if I can even dot that in there, you see that the area that is marked here is the big square minus a little square. In other words, x squared minus a squared. Now, I'm going to put a few more dots in here because that's going to lead me to my second picture. And so if I mark the dot there, this region up here is size a, so this little part in here is x minus a, of course. And the same way goes with this distance here as x minus a, because the total distance is a, and you subtract away, total distance is x, and you subtract away little a. And I will even shade in this part to distinguish it. All right, I think that's enough information. Now over here, I'm going to redraw parts of this. The first part up to the dotted line there, and then down here. Let me finish this off. There you see the picture that we had before. These two are the same picture. This is a big square minus a little square. Now what's going to happen over here? Well, this side is of size x minus a. Remember, this part is x. And what I do is I take this piece and I move it down here. And I attach it to the bottom, just like that. Now this was of size a because this was of size a. And this distance here was x minus a, so that this distance now here is x minus a. This is the shaded region. All I did was take it from here and I moved it underneath. Now, what is the distance along this long side? Well, it's x plus a. And what's the distance along this side? X minus a. And if you multiply these together, you have the area of this rectangle, which is the same as this area of x squared minus a squared. In other words, this side equals this side. I like that. That's a nice picture. Now, of course, I'm assuming that a is less than x here so that the picture makes sense. So x is greater than a here. But you understand the principle, I hope, and you've seen a nice picture to boot. All right. Well, we've looked at the difference of two squares. Now let's ask the obvious second question. What about the sum of two squares? Question mark. Well, you probably guessed something's going on here. I put a question mark. Well, what would that look like? Well, that would be some sort of binomial here times some sort of binomial, whoops, equals x squared plus a squared. Well, is there a pair of binomials for which this is true? Well, unfortunately, there's no rule yet for us. Because, why? Because it will require complex numbers, which is a set of numbers we haven't quite gotten to yet. We will in a little bit. But for the time being, we don't have complex numbers, and because we don't have complex numbers, we can't fill in this side. So this will have to remain a mystery for the time being. All right. Well, we've done difference of two squares, and now I've attempted to do sum of two squares, and I've seen where that leads me. Let me go ahead and now look at the next step up. We're only going to look at the next step up. Difference. In this case, I can do both. So difference and sum of two cubes. So this is going to be the third power. And I won't go any further than that because that would start getting not simple. In this case, if you take x minus a times x squared plus ax plus a squared, you get the difference of two cubes. X cubed minus a cubed. Now, and I won't prove this one. You can prove it yourself. You can just distribute the x over here and the minus a over here, and you'll get x cubed minus a cubed. All the middle terms will drop out. But I want to show you that we get a bonus here. This is really two formulas in one, and by thinking about it very simply, we can get the other one without having to memorize it. Here's the bonus. You don't want to have to memorize too many things in mathematics. The bonus is just replace a by minus a everywhere. So what am I going to do? Let me recopy the formula by putting a box in there for a. So it's x minus box, x squared plus box times x plus box squared equals x cubed minus box cubed. All right? And now what I'm going to do is put in the box minus a. In every place that there's a box, which represents where a was, I put minus a. And once I've done that, look what happens. Here I have x minus a minus a. That's known as x plus a. In the middle I have x squared, then minus ax. Minus a squared is the same as a squared, so that's a squared, equals x cubed, and then minus a cubed. Minus a retains its minus when it's cubed, so the two minuses cancel, and you have x cubed plus a cubed. And look at that. We have a new identity. That is the sum of two cubes. And what's different from the one above? Well, notice that there's an x plus a here, there was an x minus a there. And here there was an x squared plus ax, and down here you have a minus. And then, of course, it is the sum rather than the difference. But you don't have to memorize two formulas. That's the point here. The point is, memorize one of these, and remember that if you replace a everywhere by minus a, you will get the other one. So you don't have to work so hard. Okay. Well, now we've got the difference of two squares. Tried the sum of two squares, didn't have any luck, and we've got the difference in sum of two cubes. Now let's look at another kind of product, and these will all come under the same kind of title, powers of binomials. And I'm only going to take the small powers, the second and third power. If I go any higher, it gets to be too hard, and I need a pattern or I need a computer algebra system. But before I get to the squared case, let me note a couple things along the way, because there's going to be a pattern here that we're going to be using later in the course. Notice if you take x plus a to the 0 power, and I'll assume that we don't have x and a being 0. Take something here that's non-zero to the 0 power. What do you get? You get 1, of course. All right. If you also look at another trivial case, x plus a to the 1 power, what do you get? Well, you just get plain x plus a. Now, I put a square box around the 1 up here. I'm going to do something else here. The x has coefficient 1. The a has coefficient 1. Let me just box that in for the time being. I'll have an ulterior motive for doing this later. So you can think of this first one here also as a coefficient, but these two are certainly coefficients of x and a. All right. Now just put that on the back burner for a moment. Now let's get to the one we really want. Now, we really want x plus a quantity squared. That's the first rule that's going to be useful to us. Well, when you simply multiply it out, you get x squared plus 2ax plus a squared. And there you go. So this is a product of the same binomial twice, the binomial squared. You get this form over here. And while I'm here, I'll also mark down its coefficients, just for the record. That's a 1, that's a 2, and I have a 1 again. Okay, I'll mark that coefficients And again, I won't do anything with that for the time being. Now, why is this true? Well, the proof takes about 2 seconds. I won't do all of these, but let me just show you this one for a moment. X plus a times x plus a is, of course, multiplying x by x and then x by a. I get x squared plus xa, and then ax from there, and then a times a gives me a squared. And when I add these two together, of course, I end up with what I have up here. So, there are the squares. There is the square of a binomial. And in fact, there's even more I can say about this. Let me go ahead and say a little bit more. Notice, in this x plus a squared equals x squared plus 2ax plus a squared form, let me observe something else. I've already kind of looked at the coefficients. We'll come back to that. But notice that here I have an x squared, then I have an x, then I have an x to the 0, because that's just 1. Also notice that you can imagine I start with a to the 0, which is 1, a to the 1, a squared. So it looks like the x's go down in power, the a's go up in power, and that's true. That also helps you remember these. So let me go ahead and write this out in a huge arrow. There you go, big, big, big arrow. Okay? And this applies to this part right there. And what am I going to say? I'm going to say powers of x decrease and powers of a increase. And if you write this out this way, you'll see that. A to the 0 x squared plus 2a to the 1 x to the 1 plus a squared times x to the 0. So you see the x's go down, the a's go up. You might also notice that the sum of the powers is always 2. That's 2, that's 2, and that's 2. And that is the exponent of the binomial here. Now this is an important pattern. If you recognize this, it'll help you remember some other things. Well, once we have this idea, we can get our bonus again. Same trick as before. We replace a by minus a everywhere. And what do we get? Well, remembering that this is x plus box squared equals x squared plus 2 box x plus box squared. And then putting minus a in the boxes, like so, we end up with x minus a quantity squared equals x squared. That won't change. And then we have minus 2ax. And when you square minus a, you get the same thing as a. So it's still plus a squared. And lo and behold, you have another identity. This one came free. If you started with the original one, which I was boxed on the other page, if you started with the original one and you replace a everywhere by minus a, you get a new one. So you don't have to memorize 2 different identities. You get one. And then the other one, you know how to get it. All right, good. Well, if that works for squares, it should also work for cubes. So likewise, and this time I won't put in all the details, x plus a cubed is equal to x cubed plus 3ax squared plus 3a squared x plus a cubed. And just with what we've done before, you can verify that that's right. At least you can verify that the powers are right. X cubed, x squared, x, and x to the 0 are going down. A to the 0, a to the 1, a squared, and a cubed are going up. So the powers are correct. Now, you may not know why the coefficients are correct. They are 1, 3, 3, 1 here. Let me mark them one more time. Call them coefficients. But I assure you they are. And there's a pattern here that at some point in the course you can actually discuss. Now, if you do the same thing as before, and you replace the a by minus a, I won't go through the details this time, you get x minus a cubed is equal to x cubed minus 3ax squared plus 3a squared x minus a cubed, and you get free, right, bonus again, this new identity. So if you can take x plus a cubed and you know that particular form, you automatically know the next form. So this should make it a little more efficient for you to remember things. All right. Well, I said we weren't going to go beyond cubes, but let me at least give you a glimpse of what's to come, and we may get to at the end of the course. we could generalize, always like to generalize, to x plus a to the nth power. Instead of just 0, 1, 2, and 3, we could go to 4, 5, 6, etc. When we do that, we get something called the binomial theorem. Now, I'm hoping that by the end of the course we'll have a chance to talk about this, but we won't talk about it just now. Also, the pattern of coefficients, which I now list all together. The first one was 1, you remember. Then we had 1 and a 1, then a 1 and a 2 and a 1, and then a 1, a 3 and a 1, and then for higher powers it would continue. This is a very famous triangle. It's called Pascal's triangle, in case you've heard of it. And it is intimately related to the binomial theorem, which is how you multiply out x plus a to the n. So on that teasing note, I will leave you for that and give you a tip, and then you'll have a chance to practice some of these forms so that you can get used to them. All right, what is the tip? Well, the tip is exactly what I've been saying all along. Learn to recognize these, and I'll just call them 4 handy patterns, or you could call them identities, because that's what they are. If you replace the x and the a by anything on either side, you will always get a true statement. And you could also think of them as your vocabulary for today. Which ones am I talking about? Here are the 4 I mean. X squared minus a squared, and I'll put next to it that there's no x squared plus a squared in the real numbers. There's no factorization for that there, but there is one for x squared minus a squared. Then there's one for x cubed minus a cubed, and that's intimately linked to x cubed plus a cubed. So I put them together because if you know one, you know the other one. And then there's x plus, so these are slightly different. Let me put a bar there. X plus a squared, that is linked to x minus a squared by the same trick as before. And then finally, x plus a cubed is linked to x minus a cubed. So there you have it. 4 standard patterns that if you become familiar with will help you in doing a variety of problems we do later. They are analogous to doing the multiplication tables. So take some time to look at that now, and I'll be back in a bit. Handy polynomial products. We want to do the flip side, and we want to do something that becomes a dreaded possibility for a lot of students. Unmultiplying polynomials. The common word is factoring polynomials. So let's go ahead and look at this dreaded operation, which doesn't turn out to be as hard as you might think. Let's set the scene here. First of all, I've called it unmultiplying. That's what you want to think of this as. Taking a polynomial and unmultiplying it, giving it form, giving it structure. And I'll say that throughout this section. But let's recall some of the terminology. Remember, we're currently using the word factors. Factors are things that are multiplied. Things that are multiplied. In other words, we're using factors as a noun. Now, we also use factor as a verb. In fact, in Europe, they have a different word for it. In Europe, they use the word factorize. I found that a little odd when I saw that, but I can see that that has a point now. There's no confusion between factor as a verb and factor as a noun. Okay, so factors are things that are multiplied. We now want to factor things. So, here's the key idea with numbers. Because our notion of factoring polynomials is based on what we know about numbers. Here I'll show you an example. What you can do is 2 things that are reverse operations. You can multiply 2 to the 10th. Now that's easy, and get 1,024. Now we've seen that number before. I'll mark here that this is tedious, but it's easy. You just multiply 2 times 2 times 2, etc., 10 times. It can wear you out, but it's not hard. All right. What about unmultiply? which of course we're now going to refer to as factor, 1024. Now in general, this, although we know because we just did it, is 2 to the 10th, this is harder. Starting with a number that exhibits no particular structure and pulling this nice structure out of it is harder than going the other way. It's a general principle in life, and I'll write down a couple of things to illustrate that. Reversing a process is hard. For example, if you take a glass of water and you drink it and then you throw the glass on the floor, that's one series of operations. Now reverse the process. Take the glass of water, throw it on the floor, and then drink it. You can see that that's going to be much harder than the original way. Reversing a process is hard. In fact, using a famous phrase from a song, breaking up is hard to do. All right? So I want you to keep in mind that factoring is a generally hard process. We are only going to learn how to factor some easy things. All right, that was the key idea with numbers. Now here's the key idea with polynomials. Now polynomials is what we want to deal with. Polynomials, and the only kind of polynomials we're going to deal with most of the time, polynomials of one variable. And our variable in this course, for the time being, will be x. So here's the key idea with polynomials of one variable. Example, same thing, except now it's polynomials instead of numbers. Multiply. If I give you x plus 2 cubed, again, it is kind of tedious, but not hard to get this equal to x cubed plus 6x squared plus 12x plus 8. So again, tedious, but easy. Especially if you remember the formula for cubes that we did in the last section. Unmultiply. If you start out with x cubed plus 6x squared plus 12x plus 8, you can just see by looking at that. Where would you start? How would you, if you don't recognize it as a familiar form, how would you possibly factor this? So going from there to the fact that this is equal to x plus 2 cubed is harder. I think you can appreciate that just by looking at that. So, once again, the reason we will only discuss a few basic patterns is because, in general, factoring is a hard idea. Okay, well, why do we like polynomials in factored form? You write that down. Why do we like polynomials in factored form? That's a good question. Why bother going through all of this effort? Is it just manipulation for the sake of manipulation? Well, no. There's actually a reason for this. One reason is that the multiplicative structure, how do you like that? Multiplicative structure is revealed. You see what makes up the polynomial as a product. You might think of the pieces that you get as atoms. As I talked about prime numbers being atoms, we're now going to look for atoms that multiply out to be polynomials. So, once you have that structure, something very important happens. Simplification. And remember, we're always trying to simplify our expressions in mathematics to the point where they're so easy that we don't have to think about them anymore. So simplification of expressions becomes easy. Or becomes easier. Becomes easier. Okay? That's why we like polynomials in factored form. Because with the structure revealed, we can simplify things more easily. And if you study further mathematics, that structure will be important. Okay. Now you have an idea why we want it. How far can you go? What do I mean by that? Well, how many factors? Because as with numbers, which you know can be factored down to the prime numbers, or powers of prime numbers, how far can you go with polynomials? Well, let's go back and remember what we can do with natural numbers. For n, which was the natural numbers, let's recall what we know. The fundamental theorem of arithmetic, which we talked about earlier in basics here. The fundamental theorem of arithmetic, what does it do? It guarantees we can factor numbers from the natural numbers into prime powers. So into prime numbers, powers possibly can occur. For example, here's a nice easy case just to get you started here. 30, of course, is 6 times 5. But this part is not prime. 6 is not prime. So we can go a little further. We finally get down to 2 times 3 times 5. These are prime factors. They are all prime factors. Okay? These are the atoms, as I called them once before, of the natural numbers. Because every natural number can be, as by the fundamental theorem of arithmetic, factored into prime powers. So we ask ourselves, is there something like that for polynomials? Well, let's see. Similarly, for polynomials, in one variable, let me just remind you of that. We're only looking at those sorts. In one variable, we can factor into what are called prime polynomials. Now I have to decide what is a prime polynomial. What could that possibly mean here? Well, what was the idea about a prime number? A prime number was a natural number greater than 1 that was divisible only by itself and 1. So we need something analogous to that for polynomials. So let's go ahead and make a definition. And I think you'll see how this is going to be analogous. Definition. A polynomial, well, first of all, we don't want to deal with numbers, constants, because the natural numbers will factor into primes, but not necessarily real numbers. So a polynomial of degree greater than 0. So we're taking one that's greater than 0, which means it's not constant. I'll put that here, not constant, is called prime. Okay, such a polynomial will be called prime if it can be written, well, you probably guess what's coming up, as a product only of itself. And we have to add plus or minus 1 here, but it's the same idea. It's a product only of itself and plus or minus 1. Now, there is one thing that's different that we need to talk about. A polynomial is only prime over, put that in quotes because that's a piece of terminology, over or with respect to the number set its coefficients are in. So they might be in the natural numbers, they might be in the integers, they might be in the rational numbers, they might be in the real numbers, or later, they might be in the complex numbers. These are the complex numbers. So a polynomial can only be prime with respect to the set of numbers that the coefficients come from. So I need to illustrate this so that you have a sense of what I mean by that. And it will turn out that polynomials are prime for certain sets that are not prime for other sets. In fact, as you move up in this direction toward higher number systems, in the end, everything can be all polynomials can be factored in the complex numbers into polynomials of degree 1. But if you come back from that, that's not true for these lower number sets. So let me show you by example what I mean. Here's an example. What I want to do is factor this and remind you that we're calling that unmultiply. I want you to continue to think of it that way. And here's the polynomial. X to the 5th minus x to the 4th minus x cubed plus x squared minus 2x plus 2. Now, I'm going to show you 3 different factorizations of this, depending on the number set I allow the coefficients to be in. First of all, I could factor it as x minus 1, x squared minus 2, x squared plus 1. Now don't worry how I'm figuring out how to factor this. That's not the point here. The point is, this is a factorization. You can check it if you like. You have this factorization. These are primes Now primes here means prime polynomials, primes over z. So you notice all the coefficients here, the constants and the coefficients, are integers, but no further. Now you can look at this and say, well, x squared minus 2 can be factored further if I allow square root of 2. Well, that's not an integer, so I have to move up to another set. So if I go further and I leave the x minus 1 alone, x squared minus 2 can be factored into x minus square root of 2 times x plus square root of 2. So this can be further broken down into that. And I'll leave the last one alone. What allows that? The presence of square root of 2 allows that. So these become primes over the real numbers, because that's where square root of 2 lives. So the factorization has been made more fine. All right, I've got 3 linear terms. I still have this final quadratic or degree 2 term. Can I finally factor it? Well, you can, but we don't have the number system yet. I'll show you what it looks like. These will be primes over C, the complex numbers, which we haven't discussed yet. But x minus 1 will stay the same, x minus square root of 2, x plus square root of 2, and now I'm going to write something I haven't explained, x minus I, x plus I. I have not talked about what that I means, but trust me, it's a complex number. We'll talk about it in a little bit. And you can see that now I have this down to 1, 2, 3, 4, 5 linear factors. Well, you know, there's going to be an important theorem that has to deal with this later on. But right now, I want you to see that this initial polynomial, depending on the number system that you're in, z, r, or c, can be factored in a number of different ways. So the meaning of the word prime depends on the number system you're in. That's what you want to keep in mind. Okay, well, now since we're looking at forms for factoring, let's go ahead and look at polynomial product identities. That's from the last bit. Identities, and we'll revisit them. So we'll call this revisited. Now I'm going to do a typical thing that's done in mathematics. I'm going to take a given identity, which goes from left to right, and I'm going to read it from right to left, which gives me a new identity. So, read them backwards. This is something students often forget. If you read something backwards, so they serve double duty, depending on which way you read them. So, for example, let me indicate that there are 2 directions going on here. The direction for multiply, since we're interested in factoring, the direction for multiply will be from, I get my arrow in here, from right to left. Okay? And the other direction will be unmultiply. So let me write that down. Unmultiply, which of course means factor. That direction will be from left to right. Okay? So I've got multiply and unmultiply. All right. Well, the first one I'll look at is x squared minus a squared. Looking at it with the x squared minus a squared on the left, unmultiplying it, it becomes x minus a times x plus a. You notice I've simply reversed the 2 sides. Then let's look at the cubes. X cubed minus a cubed. If I write the x cubed minus a cubed over here, I can factor that as x minus a times x squared plus ax plus a squared. I can also factor its companion, x cubed plus a cubed, similarly, into x plus a times x squared minus ax plus a squared. Now see, going from right to left is multiplication. That's what we had before when we saw these as identities. Now if we go from left to right, we have factorization. So you already know these. There's no need to learn a new set. Let me show you even more on the next page. Once again, multiply is going from right to left, and unmultiply, for which the proper word now is factor, goes the other direction, from left to right. So, I can now give you the other ones we had. We had x squared plus 2ax plus a squared. That's x plus a quantity squared. Likewise, for the difference, we had x squared minus 2ax plus a squared, and that was x minus a squared. So here is a pair, and by reading them backwards, we have a way of taking these trinomials, these have three terms, trinomials, and making them into a product, in fact, nice squares of binomials. We could do the same thing for the cubes, just for the record here. X cubed plus 3a squared x plus 3a squared, ax squared was the first one, I'm sorry. Should have remembered my own rule, right? X cubed, x squared x plus a cubed is going to equal x plus a cubed. And likewise, its companion here, x cubed minus 3ax squared plus 3a squared x minus a cubed will be x minus a cubed. Now, I wrote all of that out, but again, since you've already seen them as product rules and with luck learned them, then all you have to do is consider them backwards and you have a series of factoring rules. So again, this is nothing new. This is looking at the old with new insight. There is one useful case that didn't fall above there. At least it didn't fall in its full generality. Useful case. Suppose you have a standard quadratic or degree 2 trinomial. So you have a squared term, an x term, and a constant perhaps. When this factors, if it factors nicely, it will factor into two binomials. I'll just put boxes there for right now. Two binomials. Now how do you fill the boxes? Frankly, the best way to do it is guess and check and use experience. Because you know, for example, that the first two here, if you put things in order, are going to have to give you the first term, and the last two multiplied together will have to give you the last term, and then you just guess and check a little bit on the middle terms to see what needs to be there. When you do this in practice, you quickly get a pattern down, and you can experiment with this on your own. You'll have a chance to do this in a little bit. All right. Well, now let's go ahead and pull all of this together. We've got a lot of information. Let's go ahead and pull this all together and call this a general technique. Technique for factoring a polynomial. Now, there are probably other techniques out there. There are lots of specialized techniques for certain kinds of polynomials. But the fact is, there's only a small core of things that you need to know. And if things get really difficult, you should go to a computer algebra system. First of all, you need to decide what number set is desired. Do you want your factors in the integers? Do you want them in the real numbers? Do you want them in the rational numbers? Do you want them in the complex numbers? You need to decide how far to go. Then what you want to do is factor out. Here we're using factor as a verb again. Factor out all factors. Now factor is being used as a noun. Common. Common to every term. So when you look through a polynomial, there may be things that are common to every one of them. There may be a number you can factor out. There may be a power of x you can factor out. Do that first. Makes your life easier. Then you want to consider the identities above. All those identities that we looked at a moment ago. Now this should be a whole collection of these in your mind that you can check. Then finally, for hard cases, frankly, use a computer algebra system. That, by the way, is usually abbreviated CAS. Now, in this course, none of the problems that you face will be hard enough to require a computer algebra system. So, really only these first few, these three bullets here, are the kinds of things that you need to look for. I will do a few examples now to give you a taste of this. For example, take 6x squared plus 9x. Well, you just look at that for a moment and you say to yourself, the first thing I want to look at is, are there any common factors? Now, I'm going to factor this as far as I can, so that decision has already been made by me. But I need to see what's common here. Well, you can see that a 3 is common to these two. Also, an x is common. So 3x can be factored out, and let's just see what's left. I'm left with 2x here plus 3. Now, there's nothing I can do to take this any further. This is a nice linear term, and this is also a linear term. So I'm finished as far as this goes. So that was easy. Let's do another one. 2x squared minus 4x plus 8. Now, this is a trinomial, takes a little more effort. I know from the last fact that this is going to factor into a binomial times a binomial. Now, the question is what? And will it be nice numbers? Well, this is a nice textbook problem, so it's going to be nice numbers. But there is something you can do first. See, this is the first instinct that you have. But there is something that you missed if you thought of that first. What did I do up here? I looked for common factors first. I should have done that here because I see that 2 is common. So first I pull out 2, and I'm left with x squared minus 2x plus 4. So rather than go to this stage first, I take the easy stage first. I take the 2 out. Okay, now I look at this. That has no common factor, so now yes, that will turn into a binomial times a binomial. And I can make some judicious guesses. I expect there'll be an x there and an x there. And if I want to fool around, I can try a 1 and a 4 to multiply out to be 4. I can try a 2 and a 2. Those are the only nice numbers that are going to work right now. You might say, well, what about all the square roots possible or the other real numbers that multiply out to be 4? Yeah, but that's getting to be too hard for me. So, since I don't see any easy way to do this, I'm going to stop with this previous stage. Now, if we turn out to study this later on, you'll see that this cannot be factored in the real numbers, so my stopping there was legitimate. Okay, let me take one more that goes a little further. X to the 4th minus 16. Well, we don't have any rules for 4th powers, but we do have rules for square powers. So if I rewrite this as x squared squared minus, remember 16 is 2 to the 4th. This is 2 squared squared. Now, ignoring the fact that the insides are also squared, just look at the outside. I have box squared minus box squared. That's a difference of 2 squares, right? Difference of squares. Well, that means I have a rule for that. X squared minus 2 squared, remember it's the inside minus the inside, times the inside plus the inside. This first one is again a difference of 2 squares. In fact, real squares this time. X squared minus 2 squared. So this will be x minus 2 times x plus 2. This one, however, is a sum of 2 squares. And we have no rule for that, as I told you. So I stop there, and I am happy with that factorization. I have 2 nice linear terms, 1 quadratic that, if I were in the complex numbers, I could reduce to linears, but I'm quite happy with this factorization. So there's 3 examples for you to look at. And the kind of experience that tells you when to stop is the kind of experience you can only get by doing a lot of these. All right, time for some tips. Tips. First of all, leave polynomial expressions factored as much as possible. So leave polynomial expressions factored whenever possible. Why? Because the structure is clear. Do not succumb to what I like to call the student's multiplication disease. This is where when a student sees something that is multiplied together, especially with polynomials, they multiply everything out. Somehow that seems to make them feel better. In fact, it makes things much, much harder. So always leave things factored in that nice product form. Don't succumb to this disease. Example of the disease. X plus 1 to the 4th is much nicer than the same thing multiplied out, which is x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. Right? This is nicer because it's factored. The structure is clear, it's simple. This is opaque, unless you happen to recognize the form, and in most cases, you won't. So, on that happy note, we'll pause, and you can try and factor a few things on. All right. Now you've had some experience factoring, I hope. Another topic that turns up that involves polynomial factoring, and is another way of making things easier, and you will see later in the course that this is true, is something called completing the square or completing a perfect square. So let's go ahead and look at what that is, and I'll do this by example. I'll give you 3 examples. So here's the idea before I do any of the examples. Here is the idea behind this. ax squared plus bx plus c. We would rather have that in a form where you might have a constant here, but you have a perfect square of a binomial, and you might have another excess constant. But here is the perfect square that is referred to in this method. So we want to rewrite this unformed trinomial, this trinomial of degree 2, into something that has some constant perhaps, a nice perfect square, and some other constant. All right? It will turn out that this is a very useful technique, and we might as well review it now. And I will do this again by example. I will do 3 examples. So let's go ahead and look at that. Example number 1. And all of these will be complete the square, because that's the way these things are phrased. Complete the square, and here it is. X squared plus 5x plus 4. Now it always pays to take a moment and see if it's already a square, because if it's already a square, there's nothing to do. This one's not. So here is the technique. The problem is that the 4 here is not the right number to make this whole thing into a perfect square. So I will simply set the 4 out of my way and put the correct number in there, being very careful to compensate for it so I don't change things. All right, let me explain what I'm doing. X squared plus 5x, and I'll put the 4 way over here. Okay? What I want to do is add in here the right number to make this part a perfect square of a binomial. Now, how do I do that? Here's the technique. You look at the coefficient of x, and what you do is you take 1/2 of that coefficient, so 1/2 of 5, you square it, and you put it in the box. So there's the process. You take the coefficient of x times 1/2, square it, and put it in the box. Now, that has changed this expression. I've added something new. Well, if you add something new, you must compensate for it, otherwise you change the problem, by subtracting away that thing. So over here, I'll put it down here to remind you, I'm going to subtract away what I just added. So I'll subtract away 1/2 5 squared. Okay, what do I now have? I have x squared plus 5x plus 1/2 5 squared. And then over here, I can simplify a little bit, but I won't do that just yet. This is plus 4 minus 1/2 5 squared. Now this should be a perfect square by design. All right? This, in fact, will be x plus 5 over 2, if you like, quantity squared. This is by design. The design being the 1/2 times 5 squared that I did up here. So that's by design. The rest of it is just there. So let's just look at this and say to ourselves, what is this? This is, do a little scratch work here. This is 4 minus, let's see, 5 over 2. That's 25 over 4. And 4 is 16/4. So 16/4 minus 25/4. So this, in fact, can be rewritten as a minus 9/4. Now you can check the arithmetic on your own, but I've started out with this trinomial, which was not a perfect square, and I've rewritten it as a perfect square minus a constant. That's the technique of completing the square. And if you follow this method more or less, you should avoid making mistakes. Now I'm going to show you a couple of other variations on this so you can see what might happen. But this is the basic technique. All right, my next example. Complete the square. Again, And this time 2x squared minus 8x minus 5. Again, it might be worthwhile to stop and see if that's a perfect square. It is not, so I'm going to have to make it a perfect square. So in this one, there's a new kink that turns up. I first of all take the 2x squared minus 8x, put the minus 5 off to the side, as I said before. Now, I will do one other thing here. It is preferable when you're doing this, and to use the technique I had a moment ago, let me bring back that sheet. Here's that sheet I was just looking at. Notice that I had an x here without a coefficient. The original trinomial had no coefficient, or a coefficient of 1 times x squared. Now, here I have a 2. What does the method require at this point? Well, factor the 2 out. So I'm going to first of all rewrite this as 2 times x squared minus 4x in parentheses and put the 5 outside. So I have factored the 2 out of these two objects. Now I go in here and I do the same operation I did before. I want to add the correct number here to make this a perfect square. So I take the coefficient here. I take 1/2 of that coefficient minus 4. I square that object and put it in the box. Well, I now have changed the problem again. But I've changed the problem by putting a number within the parentheses, and remember it's multiplied by 2. So what did I put in here? Let's just simplify this for my work over here. 1/2 of minus 4 is a minus 2. Minus 2 squared is 4. The 4 is inside the parentheses, so I multiply it by 2. So the net change to the equation is that I have added 8. In order not to change the equation, I have to subtract 8. Okay? So minus 4, this is the term I add. That's minus 2 squared, that's 4, but it's inside the parentheses. So times 2 is 8. That is what I've added, so I must subtract it. Well, now I'm done, because I have 2 times x minus 2 squared. Remember, 1/2 of minus 4 is minus 2. And then the minus 5 and the minus 8 give me minus 13. And there I am. There's the square. Okay? So this is something that you want to practice. All right, let me do one more that we will see when we talk about circles. Example. Complete the square in both x and y. So this is one that has two variables, x squared plus y squared minus 2x plus 4y minus 4. So this will turn up, as I say, when we talk about the equations of circles. So again, we follow the same procedure, except we just have two variables to do it on. So I'll isolate things, bring my x squared and my minus 2x together, leave a space in the parentheses, plus my y squared, which is here, plus 4y, leave a space, and then there's the minus 4 out at the end. So I put all my x's together, all my y's together, and my minus 4. And the parentheses this time are just for my peace of mind, to keep things together. They don't have any bearing because there's no constant multiplied out front. Again, I want to add the correct number to both of these to produce a perfect square. Well, here's minus 2. I'm going to add 1/2 of minus 2 quantity squared and put it in there. Here is 4. I'm going to take 1/2 of 4 quantity squared and put it in there. Okay, well, what is the net change then? Here, 1/2 of minus 2 is minus 1. 1 squared is 1, so I've added 1 here. Nothing out front. I've just added a 1. So subtract 1. Likewise over here. 1/2 of 4 is 2. 2 squared is 4. Nothing out front. I've added a 4. Subtract a 4. So finally, I can rewrite this as x. What did I have in here? Minus 1, quantity squared, plus y. And here I have 1/2 of 4 is 2. So it's plus 2, quantity squared. And then minus all of this. That's minus 9. So there I have it. This time I have 2 squares. This one and this one instead of 1. But again, the principle was exactly the same. So, I hope with these 3 examples, you've had a chance to see how this is going to work. Why don't we pause and you try a few of these.